Synchron. 3, 2, 1, go. Hi everybody, and welcome to this detailed introduction to a piece of software I devised and now release as open source free software to contribute making a better tomorrow. It's called Lagrangian Dynamics New Flavour Simulations, designed to simulate most types of articulated bodies, such as cars, trucks, crane trucks, and all the like. A comparatively very small and simple piece of software, whose use can be understood by anyone. An understanding to which it's my intention now to provide substantial documentation in a way as friendly and human as possible. So, in order to make it easier for me to edit the video, this video, for watching some footages of the examples, sample programs implemented using this piece of software, I suggest to watch the preview video, which features some of footages of different example programs running. But even better, I suggest to download some of the examples and try them on a computer interactively. Well, this piece of software has undergone quite some evolution. In fact, I devised it quite some years ago, around 3 or 4 years ago. And later on in its development, I had attempted to encapsulate it into a C++ class, but then since it didn't go very well, the process of encapsulation, I reverted to the standard C version, and that's the reason why I proposed that one. And the two main reasons are the fact that the final validating tests, some of which I had brought on recently, I did all on the standard C version. This is one reason, and so that should be the most reliable and so on. And the other reason is that this way, by releasing the standard C version, which anyway is not so large as to make it too much confusing. So releasing the standard C version and referring to that one won't shadow the simple concepts underlying the simulation algorithm, which is implemented there, and the concepts underlying the very Lagrangian dynamics and its new flavor, which are at the heart of this piece of software, which is my intention to present now. So, let's get started. End of record. Three, two, one, go. This is not the right context and anyway there wouldn't be enough space to do a detailed discussion of Lagrangian dynamics. But for the eventuality that you are not familiar with it already, to some extent at least, in order to avoid making you feel abandoned in front of some difficulty, and in order to guarantee that you can understand to an excellent degree all what follows later about the usage of this software for the simulation of articulated bodies, since it's all based on the Lagrangian method, even if on a modified flavor of it. It's my intention now to make a quick, let's say, quick but very strong reinforcement about what one has to know, or at least have an idea of, about the Lagrangian dynamics, considering that as we will introduce it very soon, but a bit later, but anyway soon, since the equations of motion governing this in this framework, the motion of the articulated bodies, we can start with we can start by revisiting some of the typical classical two-dimensional examples and all the theory underlying it, but with a little bit of coloring which shall help us drag towards drag us towards a smooth and flawless transition to what the new flavor of the Lagrangian dynamics has something different. Okay, most of the differences are in the so-called parametrization process, but don't worry. And don't worry if something is not clear here. Eventually, towards the end of this introduction, the whole video, the video introduction as a whole, all doubts should hopefully disappear. And anyway, after you can consult other material on Lagrangian dynamics. Case in which this small introduction and the knowledge of, to some extent, of the usage of this piece of software will give you a very solid grounding, which you can grasp and hold as strong as needed to avoid being confused by the possibility that different materials on Lagrangian dynamics explain things a bit maybe differently, use a notation a bit different, and have a different style. We know that those are some practical problems which are difficult to avoid, but we are trying to contain these problems. So, let's go. Let's get started. We have, let's start with some two-dimensional introduction and revisit some typical two-dimensional problems. from the point of view of what we are going to do, in most problems of Lagrangian dynamics anyway, we have a set of points, material points, and in a two-dimensional space. Or think it already three-dimensional if fact of thinking in two dimensions troubles you. Okay, set of points, a limited number of points, some points here, each of which have a coordinate pair or triplet if we are in three dimensions. I will be using this notation to denote pair or triplet of coordinates of a point. This way, an x underscored and numbered. Very fine. In the case of an articulated mechanism, of course, these points are not allowed to float around. Some may be allowed to, but as far as we're concerned, in that case, it would anyway default to the Newton's second law, and that would be fairly easy to deal with. But when there are springs, we would have to introduce complications which with Lagrangian dynamics are not there. So it's helpful for us in any case as far as most practical problems are concerned. So let's start with an articulated body. To avoid accidentally thinking too much the old way of Newtonian dynamics. We have a reference frame, x epsilon, all perpendicular, of course. And we have a fixed point here. We have a rotating joint, two-dimensional, another rotating joint, and we have another point, m2, x vector 1, x vector 2, and we have some generalized coordinates, as many degrees of freedom the system has. This has 2 DOFs for short, and that's all. We have come so far, and with this at hand, we could already do an animation. I'd like you to grasp and imagine. Your imagination here is sufficient. We consider that this vector of generalized coordinates, but we'll become familiar with notation, is a function of time, varies with time, and maybe it's the interpolation of some points, some sample points at different times. We can do an animation. But as we are going to introduce right in a second, the Lagrangian dynamics can be considered, the equations of motion, can be considered as a system of course, system of as many equations, as many degrees of freedom the system has, which says how to animate the system, how to vary in time the value of the generalized coordinates, so that the motion of this system, this set of points, according to the constraints that there are, all, let's see, we must know for now, holonomic constraints. Don't worry what that means, but holonomic they are called, moves according to the laws of Newtonian mechanics. And we are now at a very important point. Let's take a break here for allow you to think about what I have said. Meanwhile, I draw you a couple of other examples and introduce some more conventions. In general, we don't use angles or so for like angles like this for denoting generalized coordinates. For simple problems, yes, but sometimes we see angle, even names such as x and epsilon, but no, I even don't write them to avoid confusion. In general, we use Q1, Q2, Q3, and we call the set defining the configuration of the system, defining it fully, the vector of generalized coordinates, okay, denoted as Q. This is a vector which has as many parameters, as many degrees of freedom the system has. If you don't get confused on this notation, you are fine, okay? So when we repeat x to denote the triplet of coordinates of each point, each material point constituting our dynamical system. These are points, material points. These are the generalized coordinates. And this is the most basic notation. Okay? So this should be the reference for the whole introduction video and other possible reinforcement material I will be producing on the subject. X eth, epsilon eth, z eth, x vector eth. Set of points according to this. Each has a mass, its own mass, each of these points. So, fix the idea. Let's take another break and illustrate you some other typical articulated mechanisms, so that then we can start and go a bit more quickly. For example, we have typical completely frictionless or with friction, but the wheels usually are maybe confusing, but the wheels are just considered perfect jointing mechanisms here, so that we can consider this little carriage just a single material point of coordinate x vector 1 sliding on a perfect surface in one single direction. We are in 2 dimensions. This is just right left, to which is attached with a rotating joint another point M2, and we have an angle here, but we could have taken the angle also here, since we have originally in the Lagrangian dynamics we have plenty of freedom in the choice we make about how to parameterize the system. The process of defining the positions of each material point constituting the system is a function of the vector of generalized coordinates. This is Q2, and the position on X here is, let's choose it, Q1. It's called parametrization. This is parametrization. Very simple concept. This is another example. It could have been on an inclined plane and so on, but this parametrization requires just a little bit of creativity and so on. Well, I now suggest to look at some other typical examples, but we must make a step forward. This is going to be new, but what is universally true for our simulation software is that we have a set of points. Let us remain in the 2 dimensions now, but we will quickly jump to 3. Each point constituting our articulated mechanism, even if there may also be 3 points, like let this be free, okay, M1 be free. So we are general attached with a spring to a fixed point. It could be the center of the reference frame or wherever. And some other articulated mechanisms, a double pendulum here with these coordinates. So we have Q1, Q2, the generalized coordinates, which here corresponds to simply x epsilon, Q3, Q4, here intended as angles, and so on. Okay, jointing mechanism, free, nothing. Rotating joint, M3, 4, I almost lost the count, don't worry. M1, M2, M3. We have 3 points, x vector 1, x vector 2, x vector 3. Material points with respect with masses M1, M2, M3. Here is a better figure. We have our dynamical system made of m material points, and we have n degrees of freedom, so we have our vector of generalized coordinates. In this framework, we now set down some rules which are a bit new with respect to the traditional approach. Each material point is rigidly tied to a reference frame, and so we have to simply make a list of which point is tied to which reference frame. Of course, at maximum there can be as many reference frames, as many material points there are in our dynamical system, but there can be also less, and that's most often the case. But let's progress gradually. It's simply sufficient to make a list of which material point is tied to which reference frame, which is a triplet of versors. In 2 dimensions we have only P and Q, each of which have, well, it depends, 2 or 3 coordinates, but even if there are 3, one will be completely useless. And if we are in a 3-dimensional system, we can have we have P, Q, and R versors. Or generally, a versor, of course, depends on the vector of generalized coordinates, even if the contribution of some of them may be null. So, let's go on. We make a simple list of each point to which reference frame is tied to. And so on. Now, you may have thought that, you probably have noticed that this is a little bit sort of overkill, because why have we started to complicate the things by introducing reference frames when in this example in each reference frame there is barely one single material point? It's a sort of overkill. Well, now comes the step which makes everything come together into a coherent picture. In one reference frame we can have as many material points as many you like. So if we have a reference frame like Q2 and P, of course they have to be perpendicular, for example, like this, we can have in it as many points as we want. And what does this resemble? What is this? Now I also make the effort to say that they have also a center. My drawing is not very nice, but whatever. Each reference frame has a center, a geometric conventional center, and there we have the points which are tied to it. And of course here we can have a list of as many points as we want, as far as, of course, a point can belong only to one single reference frame, because it must be absolutely univocous. This is logic, this is cause and effect. And of course the total number of points are n. the total number of points are n material points. Very fine. So, essentially, we in this framework, which the software proposes, but we'll go into further detail later soon, is structured so that it assumes that there are m material points constituting the dynamical system, the articulated body to be simulated, and there are a number of reference frame minor or equal to the number of material points, to each of which a subset of the total number of material points is tied to. And if we think to the definition, what we have here is nothing but the definition of an articulated body as being constituted by a set of rigid bodies. Because as soon as we assume that to each reference frame at least 2 points are tied rigidly in 2 dimensions, we have a rigid body. If we assume another more in 3 dimensions, we have a true rigid body. That's the idea. The only thing is that here, in this framework, in this set of assumptions, a rigid body is a set of points rigidly tied to a reference frame, whether 2-dimensional or 3-dimensional, according to the system we want to simulate. A reference frame which has a geometric center and an orientation. In 2 dimensions is, of course, 2 coordinates for the position of the reference frame and an angle for the orientation, while in 3 dimensions it's a triplet of coordinates of the geometric center and 3 parameters for the orientation, something to which we'll come very soon. So, in the classical framework, it was implicitly assumed in such a parametrization the fact that a point is tied to a reference frame which can have an orientation which may depend or may not on a certain subset of generalized coordinates, such as here, for example. Look at the difference. This depends on no, or well, so on. But no explicit use of the concept of reference frames was used. But this may seem now a sort of overkill complication, but we'll see that this is going to simplify our whole job a lot and prevent lots of errors due to simple, so to say, lack of attention, small errors, and so on. Whew. Okay, so we can now revisit some of the classical examples with this convention, but now I let it to you to try. I think to make it easier for me to edit the video, it's better to allege further material, the set of examples after. So let's progress to the next topic, assuming that this is now clear. Its generalization to 3 dimensions will be immediate as soon as we start discussing the usage and functioning of the software, which is basically assumed to do 3D simulations of 3-dimensional systems. 3 to
1 go. So since the simulator we are going to present now, whose usage and to some extent whose functioning also we are going to present is based on the Lagrangian Dynamics as a whole, a theoretical framework. I'd like to at least outline in 1 or 2 very simple sentences what it is about and what is it good for and why it's that theoretical framework, so to say, that method, in other words, at the heart of this simulator software, even if in a slightly modified formulation with respect to its classical formulation. But don't let yourself now get confused by the fact that it's at the heart of the simulator there is an alternative formulation of it rather than the classical. For now, let me review you in 2-3 sentences the classical formulation to which the modified one is similar, and not just similar but equal, the same in so to say, as much as those concepts which I'll mention here are concerned. Okay, the Lagrangian dynamics. What is Lagrangian dynamics? It's a different formulation of the normal mechanics, that which often is referred to as Newtonian mechanics, Newtonian dynamics, and it is specialized in simulating articulated mechanisms, or at least for us, let it be formulated as such. It's a whole theoretical framework which allows fairly easily to define theoretically and then provide a simulation of the motion, realistic motion of articulated mechanisms in 2 or 3 dimensions, whichever you prefer. Very fine. Now, this method or theoretical framework, or well, call it however you want, this method is based on the observation, on the concept, on the observation that well when we have an articulated mechanism, it presents some jointing mechanisms. It's constructed through some jointing mechanisms, so to say, and these jointing mechanisms perform their job of creating the articulations by exerting constraint forces, and these are constraint forces which are particular with respect to general forces which one could apply on a material point just floating freely around in a 2 or 3 dimensional Cartesian space. They are different because if we have, of course, a system made of many material points, the absolutely special feature of these constraint forces, which concretize typical jointing mechanisms, which could be the prismatic joint, the spherical joint, the universal joint for a rigid body, so a system of three or more material points tied to the same reference frame, and the have I said all of them? Prismatic joint, spherical joint, universal joint, and hinge joint. Sorry, hinge joint was the fourth, and okay, that's also the most tricky, but we'll get to that towards the end of this presentation. The constraint forces, very characteristic feature which concretize these four types of jointing mechanisms, which I have mentioned, and a few others, but which one encounters only in theoretical problems, is this, that they don't change the total kinetic energy of our system of material points, among some of which these constraint forces act. And the consequence of this is that the Lagrangian dynamics is a formulation of the dynamics of articulated bodies, which is done through a conservation law imposed on a function, the kinetic energy function, which is the total kinetic energy expressed as a function of the total number of parameters needed to define the configuration of our dynamical system, and the rates of change of these parameters, considering that there are as many parameters needed to univocally define the configuration of the system at each instance, as many degrees of freedom there are left to the multitude of material points, which otherwise would have 3 multiplied by as many material points as there are degrees of freedom. I hope this was sufficiently clear. I decided to cut in this frontal explanation because it's not so vital that all this is clear, but it's expressed as a conservation law. It's clearly a differential equation, and we'll, as the next thing, do some reinforcement on that, and then we will progress to explain how the simulator works, and finally how to use it. I will advise when there are going to be parts which one can skip at the first glance, because using the software clearly doesn't require any particular knowledge of Lagrangian dynamics, but having a minimal concept of a minimal idea of it, what I have tried to provide now is very useful, and also makes everything funnier. Makes funnier to follow everything what comes then, and to use this software, because one knows which are the strong points of this software and which are the weaker points instead. For those now, so watch the rest of the video, use the software, and so on. Well, that's it. But for those who maybe after having used for some time this software, after having implemented some interesting simulations with it, may get interested in Lagrangian dynamics gradually, as in its whole theoretical framework explained in detail. I have done years ago a video introduction to this fantastic subject. The video presentation is called The Mechanics and its Simulation, and I will reference where to be able to watch and download and have also maybe physically and on a CD, on a DVD, the video. I will reference that alongside where you find this video. The title is already there, so you can search it on the internet, and it's of course free, and that came pretty well. But of course, since I did it many years ago, and so since then I had used quite a lot as simulation software, which I am presenting here. I've certainly acquired a different point of view on the subject, and I hope I'll do also another introduction to the subject, but from a slightly different point of view, so that we have more material on the same subject, so that if one is clearer to one person, okay, use that. If the other is clearer to another people, okay, and for the other people, use that. And that's it. So we can get started with the next chapter. So 3, 2, 1, go. So the next topic is the system, the one differential equation or system of differential equations of the same type which underlay the dynamics of articulated bodies, the system of differential equations which gives the correct motion according to Newtonian dynamics with constraint forces as to how the system has to move to respect those rules. And here is the reinforcement material on this differential equation and all the quantities it deals with. If something here is not clear, you can skip it and return to it later. Hope this is going to be useful rather than confusing. Anyway, make as much attention as you can or come to it back later, because many of the things I'm going to say are unfortunately not even mentioned on most materials on Lagrangian dynamics, and this leaves a lot of fog on the subject, unfortunately, and can compromise the ability to see how, after all, it's relatively simple, especially if we consider its power for application. So, how to view the Lagrangian equation of motion or equations of motion if we have more than one degree of freedom simply. Let's start with some very basic assumptions. Think it in the context of a stepping numerical method. So we assume zero background in differential equations. Concentrate on the Q double dot part of the equation. We will show the scheme for it soon. And keep in mind that as long as Q double dot is calculated, the next step is there. This is a simple rule from moment please, I'm going to, it's a simple rule which we well know from multivariate calculus, in particular the part on differential equations, according to which each second order differential equation can be split like this, and so start to think immediately to a fashion of a numerical method, stepping numerical method like this. All numerical methods are stepping, but not all are so simple. We are fine now for what we need to do with this simple one. Any further deepening can be done by anyone without particular difficulty once this is clear. So, why is it simple? You know, this is the Lagrangian equation of motion, which is then translated to a system of, which then constitutes, so to say, a system of as many equations like this, as many degrees of freedom our system to simulate has.
Here, in this example of before, we had 4 degrees of freedom. In that thing with the carriage, the pendulum attached to it, we had 2. In the double pendulum, we had 2 degrees of freedom. A rigid body, as we mentioned, that completely free, let completely free, has 6 degrees of freedom, 3 for its conventional geometric center and its orientation. And this is it. It seems a rather ugly differential equation, but what I'll try to do now is to give a consistent reinforcement which will help to see it as simple. We have, I have picked up for you mainly 4 points which justify the fact that it's simple and gives considerable comfort once understood about on how to think about this system of differential equations and its explicit form, which, let me pick it on, 3, 2, 1, which is this, which is used in the simulator. Do you see it? Line 1 equals to this. It's him, but with the ddt term, this left term developed. This left term with the dt developed.